If you take a standard bar magnet and snap it in half, you don't get a standalone North Pole and a standalone South Pole. You simply get two smaller, fully functioning magnets, each with its own north and south. But if we zoom all the way down to the quantum level, the mathematics of particle physics paint a very different picture. The equations insist that isolated single-pole particles, called magnetic monopoles, absolutely must exist somewhere out there. The theoretical physicist Paul Dirac calculated that the basic rules of nature actually demand the existence of these solo magnetic charges. This creates a direct conflict with our observations. Despite decades of scanning the skies with incredibly sensitive detectors, nobody has ever found a single monopole. Our best mathematical model of the Big Bang requires them, yet the observable universe is empty of them. To understand where these monopoles were supposed to come from, we have to rewind to fractions of a second after the Big Bang. At that precise moment, the universe was an intensely hot, microscopic singularity, where all the forces of nature, gravity, electromagnetism, and the nuclear forces, were merged into one unified field. As space rapidly expanded, the universe cooled, triggering a phase transition. The extreme heat dropped, forcing those unified laws of physics to violently fracture and split apart into the separate forces we experience today. This diagram shows the phase transition. A perfectly smooth field shatters into broken geometric domains, like water crystallizing into ice. The intersections where these domains meet form literal cracks in spacetime, and the math says each defect spawned a dense cluster of magnetic monopoles. Given how rapidly the early universe cooled and fractured, it should have been flooded with billions of these particles, which makes their total absence today a glaring hole in our understanding of physics. By 1979, a postdoctoral researcher named Alan Guth became entirely consumed by this exact contradiction. He needed to figure out a physical mechanism that could hide or remove these monopoles from the cosmos. On a Tuesday morning in December 1979, Guth woke up and immediately began writing out a new set of calculations. He raced to his office at such a frantic pace that he actually timed the commute, recording it at exactly 9 minutes and 32 seconds. Today, you can see the notebook where he recorded this math at the Adler Planetarium in Chicago. At the top of the page, he wrote the words "spectacular realization" in all capital letters. What Guth had sketched out was a completely new mechanical phase in the birth of the universe, discovered accidentally during his attempt to clear up a niche particle physics problem. He called this new phase cosmic inflation. It proposed that in the microsecond immediately following the creation of the monopoles, space itself underwent a violent, exponential burst of outward expansion. This animation demonstrates how that expansion interacted with our dense soup of monopoles. As the grid representing space expands in all directions, the particles are violently stretched apart. The monopoles were never destroyed. They were just swept up in the expansion and diluted across a volume and space so large that the distance between any two of them became practically infinite. Today, there might only be one or two left in our entire observable cosmic bubble. By applying the mechanics of cosmic inflation, Guth reconciled the mathematical requirement that monopoles must exist with the observational reality that our sky appears empty of them. While Guth designed this mechanism specifically to hide monopoles, other physicists quickly realized his math resolved several other stubborn cosmological paradoxes simultaneously. The most obvious of these was the flatness problem. For decades, astronomers were baffled by the observation that the large-scale geometry of the universe appears perfectly flat, defying early predictions that it should curve back on itself. This geometric model illustrates how inflation handles that curvature. When you take a highly curved circular boundary and expand it outward exponentially, any localized segment you observe straightens out until it appears perfectly flat. Cosmic inflation supplied the exact stretching mechanism necessary to take a tightly curved microscopic early universe and flatten it out to the precise state we measure today. And the theory went on to answer a deeper question: why the universe is filled with stars and galaxies, rather than being a uniform empty void. Right before inflation began, the universe was filled with roiling microscopic quantum fluctuations. The speed of the expansion caught that chaotic quantum foam and instantly froze it, scaling those microscopic ripples up to a macroscopic size. Those suddenly frozen density ripples became the gravitational scaffolding of the cosmos. Over billions of years, that scaffolding exerted the pull needed to collect drifting gas, and build every galaxy we see. The effort to explain why a single particle was missing resulted in the physical explanation for how matter clumped together to form every star and galaxy in the universe.